Microsoft Fabric Data Engineering DP-700 Masterclass, the complete roadmap to build, secure, monitor, and optimize enterprise data solutions.
Hello and welcome. In this complete Microsoft Fabric Data Engineering Masterclass, we will use the DP-700 certification path as the learning roadmap, but the focus is on teaching Microsoft Fabric as a real enterprise data engineering platform. You will learn how to ingest data, transform data, build Lakehouse and warehouse solutions, use Spark, SQL, PySpark, and KQL, orchestrate pipelines, implement real-time intelligence, secure data, monitor workloads, optimize performance, and manage Fabric environments. The goal is not just to recognize feature names, but to understand when each Fabric capability should be used and how the services work together in production. By the end, you should be able to reason through architecture scenarios, choose the right data ingestion and transformation pattern, and build solutions that are secure, reliable, scalable, and ready for analytics. Microsoft Fabric is a unified analytics platform that brings together data engineering, data integration, data warehousing, real-time analytics, data science, business intelligence, and governance into one SaaS experience. In older architectures, teams often used separate platforms for data lakes, Spark clusters, ETL pipelines, SQL warehouses, streaming systems, reporting models, monitoring tools, and governance tools that created duplicated data, inconsistent security, multiple copies of the same business logic, and complex operations. Fabric reduces this fragmentation by giving teams a shared platform centered on OneLake. A Fabric data engineer must understand how each workload fits into the bigger platform because successful solutions usually combine lakehouses, data factory pipelines, Spark notebooks, warehouses, Eventstreams, Eventhouses, semantic models, and governance features, rather than using one tool alone. OneLake is the foundation of Microsoft Fabric. It acts as one logical data lake for the organization, giving Fabric workloads a shared storage layer. Every workspace can contain items that store or reference data in OneLake, including lakehouses, warehouses, mirror databases, event houses, and semantic models. The important idea is that data can be organized across workspaces and domains while still participating in one unified storage and governance model. This helps reduce unnecessary copying and makes it easier for teams to share trusted data products. For a data engineer, OneLake is not just a place to store files. It is the architectural layer that enables lakehouse tables, warehouse storage, direct lake reporting, shortcuts, security, lineage, and cross-workload analytics. OneLake shortcuts are a key Fabric design concept. A shortcut is a logical reference to data stored elsewhere, such as another Fabric Lakehouse, Azure Data Lake Storage, Amazon S3, Google Cloud Storage, or other supported storage locations. Instead of copying data into every workspace, a shortcut allows users to access external or shared data as if it were part of their local OneLake structure. This is especially useful for data mesh architecture, where different domains own their data, but other teams need governed access. Shortcuts reduce duplication, simplify sharing, and make data products easier to consume. Engineers must still understand permissions, supported formats, shortcut target availability, and whether data should be exposed through files, tables, Spark, SQL Analytics endpoints, or semantic models. Workspaces are the main collaboration and security containers in Fabric. A workspace can include lakehouses, warehouses, Dataflows Gen2 pipelines, notebooks, Spark job definitions, event streams, semantic models, reports, and dashboards. Workspace roles determine what users can create, edit, manage, and view. A strong workspace strategy separates development, testing, and production, while also organizing content by domain or business function where appropriate. For example, a healthcare payer may have separate workspaces for claims, provider, membership, finance, and enterprise reporting. Workspaces also connect to capacity, Git integration, deployment pipelines, and item-level security. When designing solutions, engineers should think about ownership, lifecycle management, access boundaries, and how data products move safely from development to production. Capacity is the shared compute foundation that powers Fabric workloads. Spark jobs, pipeline runs, warehouse queries, semantic model operations, Dataflows Gen2, dashboards, and other workloads consume capacity resources. This means performance depends not only on code quality, but also on workload timing, concurrency, SKU size, and resource contention. A solution that runs well for one developer can slow down when many pipelines, notebooks, reports, and queries run at the same time. Data engineers should understand capacity planning, monitoring, concurrency, scheduling, and workload isolation. In production, refresh schedules should be coordinated. So heavy Spark jobs, warehouse loads, semantic model activity, and business reporting do not overwhelm the same capacity during peak usage. The Fabric Lakehouse combines the flexibility of a data lake with structured table management and analytics access. It supports raw files, structured delta tables, Spark processing, SQL Analytics endpoint access, and Power BI integration. A lakehouse is usually the best choice when data engineers need to work with structured, semi-structured, and unstructured data, perform transformations with Spark, organize data using medallion architecture, or support data science and machine learning workloads. The lakehouse includes a files area for unmanaged files and a tables area for managed delta tables. Understanding this separation is essential because raw files usually land in files first, while curated analytical tables should be written as delta tables and tables. Delta Lake is the table format that gives reliability to lakehouse data. Traditional data lake files can be difficult to manage when many users and jobs read and write data at the same time. Delta Lake adds transaction logs, asset style reliability, schema enforcement, schema evolution, time travel, and better support for incremental processing. In Fabric, delta tables are important because they can be used by Spark, SQL Analytics endpoints, semantic models, and other Fabric experiences. Data engineers should understand how to create delta tables, override tables, append records, perform updates and merges where supported, optimize storage layout, and use delta as the trusted format for analytical workloads. Delta tables are the foundation for reliable lakehouse design. The files and tables areas in a lakehouse have different purposes. The files area is the landing zone for raw data, such as CSV files, JSON files, Parquet files, logs, images, XML files, and source extracts. The tables area is the managed area where delta tables are stored and discovered. Only valid delta tables should be placed in the managed tables structure. If non-delta files or broken folder structures appear under tables, Fabric may not recognize them as proper tables. A common pattern is to copy raw files into files, use Spark or Dataflows Gen2 to clean and transform the data, and then write curated delta tables into tables. This improves organization, metadata discovery, SQL access, and downstream reporting. Lakehouse schemas help organize tables into logical groups. Instead of keeping every table in a flat list, schemas can group tables by layer, domain, or business function, such as bronze, silver, gold, claims, provider, finance, sales, or operations. Schema-enabled lakehouses include a default DBO schema, and engineers can create additional schemas for better organization. Schema naming matters because notebooks, SQL queries, semantic models, and downstream items may reference those table names. If a table is moved or renamed, related pipelines, notebooks, and reports may need updates. In larger environments, four-part naming can reference workspace, lakehouse, schema, and table, which is useful for cross-workspace Spark SQL queries and domain-oriented architecture. The SQL Analytics endpoint is automatically created with a lakehouse and gives users a read-only T-SQL surface over delta tables. This is useful for analysts and SQL developers who want to query lakehouse tables without writing Spark code. The endpoint can support exploration, views, functions, stored procedures, security patterns, and reporting access within its supported boundaries. However, it is not the same as a full Fabric warehouse. The Lakehouse SQL Analytics endpoint is read-only for delta table data, so users cannot use it as a general write engine for Lakehouse tables. To modify Lakehouse data, engineers typically use Spark, notebooks, Spark job definitions, Dataflows Gen2, or pipelines. This distinction is important for architecture decisions. Fabric Warehouse is designed for XML-first enterprise analytics. A warehouse is the better choice when the data is structured. The team prefers T-SQL. The solution requires relational modeling, and the workload depends on XML-based transformations, querying, and serving. Warehouses support loading data using pipelines, T-SQL, and Dataflows Gen2. They also support modeling patterns, such as fact tables, dimension tables, views, stored procedures, and security features. A lakehouse is stronger for raw data, Spark processing, semi-structured data, and medallion architecture. A warehouse is stronger for curated XML analytics and enterprise reporting. Many real solutions use both, with the lakehouse preparing data and the warehouse serving highly structured analytical models. Choosing between lakehouse and warehouse depends on requirements. Choose a lakehouse when the solution needs Spark, notebooks, files, delta tables, raw to curated processing, data science, machine learning, or structured and unstructured data together. Choose a warehouse when the solution needs full T-SQL development, SQL-based transformations, dimensional modeling, structured data, and enterprise BI serving. If the data is messy, large, changing, or semi-structured, the lakehouse is usually a better starting point. If the data is already clean, relational, and ready for SQL analytics, the warehouse may be the right serving layer. A strong Fabric engineer does not treat Lakehouse and Warehouse as competitors. They are complementary workloads that can work together through OneLake. The medallion architecture organizes data into bronze, silver, and gold layers. Bronze stores raw or nearly raw data exactly as received from source systems. Silver contains cleaned, validated, standardized, deduplicated, and enriched data. Gold contains business-ready data optimized for dashboards, semantic models, machine learning features, regulatory reports, and decision-making. This layered design improves traceability, data quality, maintainability, and governance. It also makes troubleshooting easier because engineers can identify whether an issue came from the source, the cleaning logic, or the business transformation logic. In Fabric, medallion architecture can be implemented with Lakehouse schemas, folders, tables, notebooks, Dataflows Gen2, pipelines, and semantic models. In a healthcare payer example, bronze might contain raw claims, eligibility, provider rosters, pharmacy transactions, prior authorization records, and care management extracts. Silver might standardize member IDs, normalize provider identifiers, validate diagnosis and procedure codes, remove duplicate claims, and apply business rules for date ranges and claim status. Gold might calculate total paid amount, denial rates, utilization by service category, member risk features, provider performance, care gap measures, and cost trend metrics. This example shows why business users should not build dashboards directly from raw files. Raw data often contains duplicates, missing values, late arriving changes, rejected records, and inconsistent codes. The medallion design creates a controlled path from source data to trusted analytics. Data ingestion in Fabric can be done with Dataflows Gen2 pipelines, copy activity, copy job, notebooks, Spark job definitions, Eventstreams, Eventhouse ingestion, mirroring, shortcuts, and file uploads. Choosing the right method is one of the most important skills for a Fabric data engineer. The correct choice depends on source type, volume, latency, transformation complexity, coding preference, operational control, and destination. Small local files may be uploaded manually. Reference data may use shortcuts. Large batch ingestion may use pipelines and copy activity. Low-code transformations may use Dataflows Gen2. Complex transformations may use Spark notebooks. Streaming data may use Eventstreams or Eventhouse. Supported operational database replication may use mirroring or CDC-style patterns. Dataflows Gen2 provide a low-code data ingestion and transformation experience using Power Query Online. They are useful when users need to connect to data sources, profile data, remove columns, change data types, split fields, merge queries, filter rows, remove duplicates, create calculated columns, and load results into Fabric destinations. Dataflows Gen2 are especially helpful for data analysts, BI developers, and data engineers who want visual transformation rather than code-first development. They can be integrated with pipelines to support orchestration and scheduled processing. Dataflows Gen2 are not always the best choice for highly customized distributed processing, but they are excellent for many repeatable transformation and preparation tasks where Power Query skills are already available. Fabric pipelines orchestrate data movement and processing tasks. A pipeline can copy data, run a notebook, execute a stored procedure, call a web endpoint, start a Dataflow Gen2, use conditions, loop through metadata, manage dependencies, and monitor execution. Pipelines are important because enterprise data engineering is rarely a single isolated step. A daily load might need to check source availability, copy new files, validate row counts, transform bronze to silver, update gold tables, refresh a semantic model, and send a notification. Pipelines provide the visual orchestration layer for these workflows. Engineers should understand activities, dependencies, parameters, variables, triggers, retry settings, templates, run history, and monitoring output. Copy activity is a core pipeline activity used to move data from sources to destinations. It supports many connectors and can move data into lakehouses, warehouses, and other supported targets. Engineers use copy activity for schedule ingestion, large-scale movement, file copying, database table extraction, and query-based loading. It is often selected when the requirement includes low-code orchestration, custom workflow steps, source queries, destination configuration, and monitoring. Copy activity can be combined with lookup activities, parameters, control tables, and notebook execution to implement incremental ingestion. For example, a pipeline can read the last successful watermark, copy only new records, and then update the watermark after the load succeeds. Copy job provides a guided ingestion experience that is useful when users want simpler setup than a full pipeline. It can support bulk copy, incremental copy, and CDC style scenarios where supported. Copy job is a strong fit when the requirement says the user wants a wizard-driven experience, multi-table selection, initial full load, and ongoing incremental movement without building custom orchestration logic. It fills the gap between simple mirroring and fully customized pipelines. Data engineers should still understand its scheduling, source, and destination support, copy behavior, monitoring, and limitations. Copy job is not a replacement for all pipelines, but it is a productive option for common replication and ingestion tasks. Incremental loading is essential for scalable ingestion. Instead of reloading all historical data every time, the process identifies only new or changed records. A common approach uses a watermark column such as last modified, load date, or increasing transaction key. The pipeline reads the last successful watermark from a control table, extracts records greater than that value, writes them to the destination, validates the results, and updates the watermark only after success. Engineers must handle late arriving data, duplicate records, failed runs, and reruns. Good incremental design is idempotent, meaning the job can be rerun without corrupting the target table or duplicating business records. Change data capture captures source inserts, updates, and deletes more completely than many simple watermark patterns. CDC is useful when the target must reflect operational changes accurately, including updates and deletes. Some Fabric ingestion options and source systems support CDC-style movement. Mirroring can also provide near real-time replication for supported databases. Engineers must understand that watermark-based incremental loads may miss deletes unless the source stores delete indicators, while CDC can capture change operations if properly configured. CDC is powerful, but it depends on source support, permissions, configuration, and operational requirements. Use CDC when change fidelity and freshness matter. Use simpler incremental patterns when append-only or update-only logic is sufficient. Apache Spark is the main distributed processing engine for large-scale Fabric data engineering. Spark uses a driver, executors, partitions, tasks, and execution plans to process data in parallel. It is especially useful for large transformations, joins, aggregations, complex data preparation, machine learning feature engineering, and delta table operations. Spark uses lazy evaluation, which means transformations are not executed until an action occurs, such as writing data, displaying results, counting rows, or collecting output. Engineers should understand this because performance and errors may appear only when Spark triggers execution. Spark is powerful, but it requires careful attention to data layout, partitioning, shuffle operations, memory, libraries, and cluster configuration. Spark DataFrames are the primary abstraction for PySpark transformations. A DataFrame is a distributed table-like structure with name columns. Engineers can read CSV, Parquet, JSON, Delta, and other supported formats into DataFrames. Then filter records, select columns, join datasets, aggregate values, create derived columns, remove duplicates, apply window functions, and write results to delta tables. DataFrame operations are optimized by Spark and are usually better than row-by-row Python loops. Common PySpark operations include read.format, load, with column, filter, select, group by, AGG, join, drop duplicates, write.format, mode, partition by, and save as table. For DP-700 readiness, users should be comfortable recognizing common PySpark patterns and understanding what they do.
Spark SQL allows engineers to use XSQL syntax inside Spark notebooks and jobs. It is useful for creating temporary views, joining tables, aggregating data, filtering rows, and creating curated datasets. Spark SQL is not the same as the Lakehouse SQL Analytics endpoint. Spark SQL runs through Spark and can participate in transformations and writes when used with Spark code. The SQL Analytics endpoint is a read-only serving endpoint over Lakehouse Delta tables. Engineers should know where their SQL is running because capabilities and performance behavior differ by engine. Spark SQL is often used in silver and gold transformations, while SQL Analytics endpoints are often used for exploration, reporting, and semantic model support.
Fabric notebooks provide an interactive development experience for code, documentation, visualizations, and data exploration. Engineers use notebooks to ingest data, inspect files, create delta tables, validate transformations, build medallion layers, and perform advanced analytics. Notebooks can be connected to lakehouses and can run PySpark, Spark SQL, Scala, and other supported languages depending on the runtime. They can also be scheduled or called from pipelines. Good notebook design includes clear sections, parameters, reusable functions, validation logic, and controlled outputs. Poor notebook design hard-codes paths, mixes experiments with production logic, lacks error handling, and provides no audit trail. For production, notebooks should be managed like engineering artifacts, not temporary scratch pads. Spark job definitions are useful for production-style Spark applications. They allow engineers to run packaged Spark code such as Python files, Scala code, R scripts, or jar files with arguments, Lakehouse references, environment configuration, and scheduling. Spark job definitions can be better than notebooks when the logic is mature, application-like, and should run as a controlled job rather than an interactive document. They are also relevant for structured streaming jobs, where retry policies and long-running behavior matter. Engineers should understand when to use a notebook for development and exploration and when to move logic into a Spark job definition for repeatable production execution. Fabric environments help manage Spark configuration and libraries. An environment can define Spark settings, runtime behavior, custom libraries, and compute choices that are reused across notebooks and Spark job definitions. This improves consistency because every developer does not need to manually install the same packages or configure the same Spark settings. Environment level settings are useful for team projects, production workloads, and control dependency management. Inline settings and libraries can still be used for session-specific needs, but production solutions should avoid uncontrolled dependency drift. Engineers should test environment changes carefully because library upgrades or incompatible package versions can break notebooks and jobs that previously worked. Delta table operations are central to Lakehouse engineering. Engineers need to create delta tables, write data in override or append mode, read delta tables, merge incremental changes, handle schema changes, and optimize table layout. Delta tables support reliability through transaction logs and support advanced analytics patterns such as streaming syncs, time travel, compaction, and schema evolution where applicable. For example, a claims pipeline might append new claim records daily, merge updates from adjudication systems, and preserve historical versions for audit. Engineers should understand when override is safe, when append is appropriate, and when merge or upsert logic is required. Choosing the wrong write mode can destroy data or create duplicates. Delta optimization improves performance and reliability. Too many small files can slow down queries and increase metadata overhead. Optimized write can help produce better file sizes during writes, while vorder improves Parquet layout for faster analytical reads in Fabric. Partitioning can also improve performance when queries frequently filter on columns such as date, region, tenant, or business unit. However, over-partitioning can create too many folders and files, making performance worse. Engineers should choose partitioning based on data volume and query patterns, not just habit. Small dimension tables often do not need partitioning. Large fact tables may benefit from date-based partitioning if most queries filter by date. Streaming data can also be written into delta tables. Spark structured streaming can read from supported streaming sources and write to delta sinks with checkpointing. Checkpoints track progress, so streaming jobs can recover without reprocessing everything from the beginning. This is useful when real-time or near real-time records need to land in a Lakehouse table for downstream analytics. Engineers should understand output modes, checkpoint locations, append behavior, schema handling, and retry behavior. Streaming jobs require operational discipline because they may run continuously for long periods. Monitoring, alerting, and restart policies are important. For DP-700, it is important to understand that delta tables can support both batch and streaming patterns. Eventhouse is the real-time intelligence container that stores one or more KQL databases. It is designed for high-volume event, telemetry, log, and time series data. Eventhouse is a strong fit when the workload needs fast interactive analytics over streaming or operational events. KQL databases store and query data using Coastal query language, which is optimized for filtering, summarizing, extending, joining, and analyzing large event datasets. Examples include application telemetry, IoT readings, call center events, cybersecurity logs, and operational monitoring data. Data engineers should recognize that Eventhouse is different from Lakehouse and Warehouse. It is optimized for event analytics and low latency exploration rather than traditional relational dimensional modeling. KQL is an important language for real-time intelligence. KQL queries often use a pipeline style where each operator transforms the result of the previous step. Engineers may use where to filter rows, project to select columns, extend to calculate new fields, summarize to aggregate, join to combine tables, and render or dashboard tools to visualize results. KQL is especially useful for time series analysis, log exploration, and event troubleshooting. Fabric data engineers should be skilled enough to understand KQL patterns and choose KQL databases when event data needs high-speed analysis. Even if most batch transformation work uses SQL or PySpark, real-time workloads often require KQL knowledge. Materialized views and stored functions in KQL databases improve reuse and performance. A materialized view precomputes and stores query results so repeated analytical patterns can run faster. This is useful when dashboards repeatedly calculate the same aggregations over large event tables. Stored functions package reusable query logic so users do not rewrite complex KQL expressions every time. For example, a telecom operations team may create a materialized view for average call wait time by minute and a stored function for identifying SLA breaches. Engineers should understand these features because real-time dashboards and operational analytics need efficient reusable query patterns, not just raw event storage. Eventstream is the real-time intelligence capability for ingesting, transforming, and routing event data. It can connect to supported sources, apply event transformations, and send data to destinations such as Eventhouse, Lakehouse, Activator, and custom endpoints. Eventstream is useful when data arrives continuously and needs to be processed with low latency. For example, customer support events can be routed to Eventhouse for real-time dashboards, to Lakehouse for historical storage, and to Activator for automated alerting. Engineers should understand event stream components, sources, destinations, transformations, and routing rules. Event streams are not only ingestion tools, they are real-time data movement and processing pipelines. Real-time dashboards provide interactive visualizations over real-time data. They help users monitor current operational conditions, investigate trends, filter data, and respond quickly. Examples include live call center metrics, manufacturing sensor status, fleet tracking, fraud event monitoring, or application performance telemetry. Engineers should understand how dashboards connect to KQL data, how filters and parameters help users explore data, and how dashboard performance depends on efficient KQL queries and properly modeled event data. Real-time dashboards should be designed for operational clarity. Users should quickly understand what is happening, what changed, and whether action is needed. Activator is an event detection and action capability in Fabric. It can monitor data conditions and trigger actions when rules are met. For example, Activator can send a Teams message when a pipeline fails, create an alert when a notebook error occurs, notify a supervisor when call wait time exceeds an SLA threshold, or trigger an action when a sensor reading crosses a safety limit. Activator is important because analytics is not only about dashboards. Many organizations need automated responses to data events. Engineers should understand how Activator connects to Fabric events and real-time data, how rules are created, and how actions support operational workflows. Fabric data warehouses support SQL-based data loading, transformation, querying, modeling, monitoring, and security. Engineers can load data into a warehouse using pipelines, T-SQL, Dataflows Gen2, and other supported methods. They can query data using the SQL Query Editor, Visual Query Editor, and external tools such as SQL Server Management Studio where supported. Warehouses are useful for relational models, dimensional analytics, and SQL-first development teams. Engineers should understand how to create a warehouse, query tables, transform data with T-SQL, model facts and dimensions, and prepare data for reporting. The warehouse is not just a storage item, it is an SQL analytics engine built into Fabric. Data loading strategies for a warehouse include full loads, incremental loads, and slowly changing dimension processing. A full load replaces or reloads the target dataset and may be appropriate for small reference tables. Incremental loads process only changed records and are better for large fact tables. Slowly changing dimension logic preserves or updates descriptive attributes depending on business requirements. Data pipelines can orchestrate warehouse loads, while T-SQL can transform staging tables into final tables. Dataflows Gen2 can also load and transform data for warehouse targets. Engineers should choose a loading strategy based on data size, source change behavior, history requirements, business rules, and recovery needs. Querying a Fabric warehouse can be done with a built-in SQL Query Editor, Visual Query Editor, and external SQL client tools. The SQL Query Editor supports writing and running T-SQL queries directly in Fabric. The Visual Query Editor helps users build queries using a graphical interface, which is useful for users who are less comfortable writing SQL from scratch. External tools such as SQL Server Management Studio can help SQL professionals work with Fabric Warehouse using familiar workflows. Engineers should understand how to query tables, create views, inspect results, test transformations, and support analysts. Strong SQL skills remain essential because warehouses are built around relational analytics and T-SQL development. Dimensional modeling is a core warehouse and analytics skill. A fact table stores measurable business events such as claims, sales, payments, shipments, clicks, or transactions. Dimension tables store descriptive context such as member, provider, product, date, location, customer, employee, or diagnosis. A star schema connects facts to dimensions and makes reporting easier and more efficient. Engineers must define the grain of each fact table clearly. For example, one row in a claim fact table might represent a claim line, not an entire claim header. If grain is unclear, measures can be double counted and relationships can become misleading. Good modeling makes reports accurate, understandable, and performant. Slowly changing dimensions preserve or update historical context when descriptive attributes change. Type 1 overwrites old values and is simpler but loses history. Type 2 creates a new dimension row for each meaningful change and usually includes effective dates, expiration dates, and a current flag. Type 2 is useful when reports must show facts according to the attribute values that were true at the time. For example, provider network status may change and historical claims may need to be reported based on the provider status at service date. Engineers should understand surrogate keys, natural keys, effective dating, and how fact records join to the correct dimension version. Copilot in Fabric Data Warehouse can help generate, explain, refine, and troubleshoot T-SQL. It can provide code completion, chat assistance, and quick actions that accelerate SQL development. However, Copilot should be treated as an assistant, not an authority. Engineers must review generated SQL for correctness, performance, security, and business logic. A generated query may be syntactically valid, but still use the wrong join, wrong filter, wrong grain, or inefficient approach. Good prompting is also important. Clear context, table names, desired result, filters, and business rules help produce better output. For production work, Copilot output should be tested, reviewed, and governed like any other code. Monitoring a Fabric warehouse includes monitoring capacity metrics, current activity, and query behavior. Engineers need to understand which queries are running, which users or processes are consuming resources, which operations are slow, and whether workload patterns are affecting capacity. Monitoring helps identify expensive queries, blocking patterns, inefficient transformations, and resource pressure. In production, warehouse monitoring should be connected to operational expectations, such as load completion times, dashboard availability, and query response requirements. Performance issues may be caused by query design, data model design, capacity limitations, or competing workloads. Engineers should investigate systematically rather than assuming the problem is only the SQL engine. Securing a Fabric warehouse includes dynamic data masking, row-level security, column-level security, and secure granular permissions. Dynamic data masking hides sensitive values such as personal identifiers from users who do not need to see full values. Row-level security restricts which rows users can access. Column-level security restricts access to specific columns, such as social security numbers, salary, or protected health information. Secure granular permissions control access to schemas, tables, views, functions, and other objects. In regulated industries, these controls are essential. Engineers should design security based on least privilege, business roles, compliance requirements, and the access path users actually use. Security in Fabric is layered. Workspace roles control broad access to Fabric items. Item permissions control access to specific artifacts. OneLake security roles can control data access at the storage layer where applicable. SQL permissions control access through SQL endpoints and warehouses. Semantic model security controls reporting access and row-level filtering in Power BI. Sensitivity labels classify data and support information protection policies. Engineers must understand that security applied in one layer may not automatically apply to every other layer. For example, SQL permissions on a SQL Analytics endpoint do not necessarily restrict Spark access to the same underlying files. Secure design must consider every expected access path. Microsoft Entra ID provides identity and authentication for Fabric. Users, groups, and service principals can be assigned access to workspaces and items. Service principals are often used for automation, APIs, and deployment scenarios. Engineers should avoid assigning permissions directly to many individual users when group-based access is easier to manage. Access should follow least privilege, meaning users get only the permissions needed for their responsibilities. In production, workspace roles should be carefully controlled, especially admin, member, and contributor roles. Viewer access may be appropriate for report consumers, while data engineers need broader permissions in development. Security design should align with team roles, environments, and compliance requirements. Data governance includes ownership, classification, lineage, quality, access control, auditing, and lifecycle management. Microsoft Purview and Fabric governance capabilities help organizations understand what data exists, where it came from, who owns it, how it is classified, and how it is used. Sensitivity labels identify confidential or regulated data. Lineage shows how data flows from sources through pipelines, lakehouses, warehouses, semantic models, and reports. Governance is especially important when data contains personal, financial, health, or operationally sensitive information. Good governance does not slow down data engineering. It makes data trustworthy and reusable. Data engineers should build governance into architecture rather than adding it after reports are already in use. Monitoring activities in Fabric gives visibility into the health of data systems. The Monitoring Hub aggregates activity across Fabric items so engineers can inspect pipeline runs, notebook runs, Spark jobs, Dataflows Gen2 activity, and other operations. Monitoring helps identify failures, long-running jobs, performance changes, and operational bottlenecks. Activator can respond to Fabric events, such as pipeline failures or notebook errors, by triggering notifications or remediation workflows. Production solutions should also maintain custom audit tables with row counts, start times, end times, statuses, source names, target names, and error messages. Monitoring is not optional. It is how engineering teams keep analytic systems reliable and business users informed. CI/CD in Fabric uses Git integration, deployment pipelines, and APIs. Git integration helps teams version supported Fabric item definitions, collaborate through source control, and review changes. Deployment pipelines help promote items across development, test, and production stages. Fabric APIs can automate parts of deployment and management. Engineers must understand that not everything is versioned in Git. Lakehouse data files and table data are not treated like source code. Metadata and supported item definitions may be tracked, while actual data must be managed through data pipelines, backup strategies, or environment-specific loading. CI/CD is about repeatable controlled delivery, not simply copying a workspace manually. Deployment pipelines support environment promotion. A common pattern is to develop in a dev workspace, validate in a test workspace, and release to production. Deployment rules and mappings help adjust connections, lakehouse references, semantic model settings, and environment-specific values. Engineers should avoid hard-coded development paths, workspace IDs, and credentials in production artifacts. Good deployment design uses parameters, variables, deployment rules, and controlled configuration. Before deployment, teams should test data quality, performance, security, and downstream report behavior. In enterprise environments, deployment should be predictable and reversible where possible. CI/CD reduces risk, supports collaboration, and improves operational maturity. Fabric administration includes tenant settings, admin hierarchy, delegated administration, user access, licensing, and platform health. Tenant settings control what capabilities are enabled, who can create Fabric items, whether external tools can access OneLake data, how sharing behaves, and which preview or workload features are available. Admins may delegate rights to capacity admins, workspace admins, and domain owners. Data engineers do not always administer the tenant, but they must understand how admin settings affect their work. If a feature is unavailable, it may be due to tenant configuration, capacity assignment, licensing, or permissions. Understanding the admin model helps engineers troubleshoot access and feature availability issues faster. Managing user access and licensing is part of operating a Fabric environment. Users need appropriate licenses and workspace roles to create, edit, or consume Fabric content. Capacity assignment determines which workspaces can use Fabric features. Admins and engineers should coordinate so development teams have the access they need while production environments remain controlled. Access should be reviewed periodically, especially for sensitive data. Service accounts, service principals, and automation identities should be governed carefully. In regulated environments, access reviews and audit trails may be required. A Fabric solution is not production ready just because pipelines run successfully. It must also have the right access model, ownership, and operational controls. Choosing the right tool is a common scenario skill. Use Dataflows Gen2 for low-code, Power Query-based ingestion and transformation. Use pipelines and copy activity for orchestrated data movement. Use copy job for guided bulk, incremental, or CDC-style copying where supported. Use Spark notebooks for code-first exploration and complex transformations. Use Spark job definitions for production Spark applications. Use Lakehouse for flexible data engineering and Delta-based medallion architecture. Use Warehouse for SQL-first structured analytics. Use Eventstreams for real-time ingestion and routing. Use Eventhouse and KQL for high-volume event analytics. Use Activator for event-based actions. Strong engineers choose based on requirements, not personal preference. End-to-end batch architecture usually starts with source systems such as operational databases, SaaS applications, APIs, files, and cloud storage. Pipelines, copy jobs, Dataflows Gen2, or notebooks ingest data into bronze. Spark, SQL, or Dataflows Gen2 transform bronze data into silver with validation, standardization, and deduplication. Gold tables are created for reporting, machine learning, and business consumption. Semantic models define relationships and measures for Power BI. Security controls protect sensitive data. Monitoring tracks failures, row counts, and freshness. Deployment pipelines move changes across environments. This architecture covers many DP-700 topics because it combines ingestion, Lakehouse design, transformation, governance, monitoring, and serving. End-to-end real-time architecture starts with event-producing systems such as applications, sensors, message brokers, databases, call center systems, or IoT devices. Eventstream ingests and transforms events, then routes them to Eventhouse for KQL analytics, Lakehouse for historical storage, Activator for alerts, or custom endpoints for downstream actions. Real-time dashboards visualize current operational conditions. KQL materialized views and stored functions improve performance and reuse. Activator rules trigger notifications when patterns or thresholds are detected. This architecture is useful when the business needs immediate awareness and response. If the requirement is only daily reporting, batch pipelines may be simpler. If decisions must happen in seconds or minutes, real-time intelligence becomes valuable. A healthcare payer end-to-end solution can include nearly every Fabric data engineering concept. Claims, eligibility, provider, pharmacy, and authorization data are ingested through pipelines, copy jobs, or Dataflows Gen2. Raw files land in bronze Lakehouse storage. PySpark notebooks standardize identifiers, validate medical codes, handle duplicates, and create silver delta tables. Gold tables calculate paid amounts, denial rates, member risk scores, utilization, provider performance, and care gaps. A warehouse may support SQL-first reporting models. Semantic models power executive dashboards. Event streams may monitor real-time authorization events. Security protects protected health information with workspace roles, item permissions, row-level security, column-level security, masking, and sensitivity labels. Monitoring and CI/CD keep the solution reliable. Performance optimization requires looking across the full architecture. In Lakehouses, engineers optimize delta tables, file sizes, partitioning, V-order, and Spark transformations. In Spark, they watch for data skew, expensive shuffles, unnecessary collects, poor joins, and inefficient code. In warehouses, they monitor query activity, model tables correctly, and tune SQL transformations. In semantic models, they simplify relationships, define efficient measures, and use direct lake appropriately. In pipelines, they avoid unnecessary full reloads and use incremental patterns. In capacity, they schedule workloads to reduce contention. Performance problems rarely come from one layer alone. A Fabric data engineer should diagnose data layout, code, model design, query behavior, and capacity together. Common mistakes include using the wrong workload, ignoring security boundaries, skipping monitoring, and building everything directly in production. Spark is powerful, but simple low-code preparation may be easier in Dataflows Gen2. Warehouses are excellent for SQL analytics, but they are not the best raw file processing layer. Streaming is valuable for low latency operations, but it adds complexity when daily batch processing is enough. Security applied only in Power BI may not protect direct Lakehouse access. A pipeline that runs without audit logs is difficult to support. A notebook with hard-coded paths is difficult to deploy. Strong Fabric engineering means choosing the simplest reliable pattern that satisfies the requirement and can be governed in production. To prepare for DP-700 level readiness, focus on practical reasoning across all major skill areas. You should understand Fabric fundamentals, OneLake, workspaces, capacity, lakehouses, delta tables, medallion architecture, Dataflows Gen2, pipelines, copy activity, copy job, Spark, PySpark, Spark SQL, KQL, Eventstreams, Eventhouse, real-time dashboards, Activator, warehouses, T-SQL loading, dimensional modeling, Copilot for warehouse, monitoring, security, governance, CI/CD, tenant administration, and performance optimization. Practice building end-to-end solutions rather than studying features in isolation. Create a lakehouse, ingest data, transform it, create delta tables, build a warehouse, query with SQL, create real-time analytics, secure access, monitor runs, and deploy across environments. Thank you for watching, and best wishes as you build real Microsoft Fabric data engineering expertise.